When talking about the atomic nucleus and different isotopes of one single element, it's almost imperative to talk about an experimental technique called mass spectrometry. Mass spectrometry is a widely used technique that tries to separate species of different mass that otherwise would be very hard to separate. Let me give you an example of why it is that we want to talk about this. Let's take neon. When we look at neon, this mass, the mass that the periodic table in neon says, that number is what we mentioned that before, is the weighted average of the different isotopes based on their abundance. So there's different kinds of neons. There is neon 20, there is neon 21, there is neon 22 with different abundances. So how can we measure, if we said that isotopes behave chemically identical, how can we measure, in what technique can we use to know how much we have of each? This is what is called the mass spectrometry. And the way this works is that one puts a sample. So imagine that we put our sample in which there is a sample of different isotopes of neon. We don't know how much, and this sample is vaporized in the mass spectrometer and ionized here. That means that now we have most probably neon plus. Okay, they are ionized. There are some electrons being removed because there is some resistance here that ionizes. They are now charges can be accelerated in an electric field, and here's some magnets. Some magnets that create a magnetic field, and if you have taken physics, you may be familiar with the Lorentz force. But what's important to understand here is that your sample of neons, in which you had neon 20, you had neon 21, and neon 22, will be reflected differently. The lightest particles will be reflected more than the heaviest ones. So in this case, the neon isotopes that are lighter will have a larger curve. So in here you will have neon 20, and here this is where the detector will hit for neon 21, and in here neon 22. Now the detector just needs to count how much of each hit the specific place, so one can count the relative abundance of isotopes. What one ends up seeing is what's called a mass spectrometer. This is the spectrum, and in this case the neon 20 is the most abundant, neon 21 is the least abundant, and neon 22 is the second most abundant. And notice that just integrating these peaks, one can calculate the abundance of each. Okay, so this is the way one can calculate this number. This number here, now we know, is the weighted average. So now the weighted average of neon will be the mass of neon 20 multiplied by 90.48 fraction plus this intensity. So the mass of neon 21 times its intensity, or its abundance, if you will, intensity of the peak, the abundance in the sample. And finally neon 22, which approximately has a mass of 22. These are round numbers, multiplied by the fraction. Okay, so take-home message is that the mass spectrometry can be used to calculate the relative abundances of your sample. And we will learn also in this module that depending on where this sample comes from, these numbers may be completely different. So it's not, if your sample comes from the atmosphere or from a geological sample, the abundance of different isotopes may be different. So we will always need a technique such as mass spectrometry to tell us the different distribution of isotopes.